Hi, I'm Zach Musgrave. This is performance in a high-throughput SQL database, real-world profiler tips. My beard is somewhat larger than you saw on your program. I'm sorry if you feel led on by the size of my beard, but we're going to keep moving. It happened during COVID. A lot of things happened during COVID that we don't talk about. Okay, so the agenda for today, after a brief introduction, the talk is split up into three pieces of roughly equal length. So first, we're going to talk about how to use the Golang profiler toolchain and walk you through some actual performance profiles of the database we're going to be talking about. Then we're going to move on to three case studies for how performance problems that we found profiling our database, trying to make it faster, and show you what those look like in your profiler, how to find and debug those, and how to fix them. And then finally, we're going to wrap up with a deep dive on the architecture of Dolt itself and talk about where we went when we couldn't squeeze any more juice out of the Golang profiler. Okay, introduction. First of all, who am I? As we've established, I'm Zach Musgrave. Hi. I lead the Dolt database project, which is an open source Golang project you can find on GitHub. It's written by a company called DoltHub, which is a 20-person startup based in Santa Monica. We have a Seattle office as well now. Before that, I was at Google. You might remember me from MemeGen. Before that, I was at Amazon. You might remember me from the Brazil build system. I'm very sorry for that. And I've been programming Go for about 4 years. My first exposure to Go was for this database that we're going to talk about. So what is this database? It's called Dolt. Dolt's the world's first version-controlled SQL database. So it's the database is like a Git repository in that you can branch it and merge it, fork it and clone it, push it and pull it. All the version control primitives you understand from Git are also applicable to a Dolt database. We're the first people in the world to do this. We think it's pretty cool. The second question we always get is, why is it called Dolt? Are you calling me stupid? I'm not. You're all very, very smart. You came to GopherCon. The reason we called it Dolt is to pay homage to how Linus Torvalds is said to have named Git. So for those who don't know, Git is British slang for an idiot or an unpleasant person. And Linus jokes that that's why he named Git. It was after himself. So we did this to pay respect to Daddy Linus. So we're talking about this as a high performance tuple store. What does that mean here? Well, okay, we're not going to claim to be the highest performance tuple store in the world. That would be dishonest and silly. When we talk about being high performance, we're talking about having built a database from the ground up and now made it possible to spool rows off of disk as fast as MySQL does and faster in some cases. So that's kind of our performance benchmark, is beating a database that's been around for 30 years longer than we have. So why is this hard? Periodically, we publish technical blogs about how we write the database, various technical aspects of writing a database. There's a lot that goes into it, obviously. And we'll often, when we socialize it on places like Reddit, we'll get comments like the one on your screen right now. WTF, why are you building your own database? Unless you have a very good reason, don't do this. SQLite is free and source, open source. Postgres is free and open source. Why build your own? LOL. So why build your own? LOL indeed. What's wrong with us? Are we stupid? Are we crazy? We don't think so. We think we have a good reason for building a database. That's why we embarked on this journey, even though we knew it was going to be a very heavy lift to get to compete with products that are 30 and 40 years greater than us. And that's what we're going to kind of talk about in the third part. We're going to dive into Dolt's architecture and talk about what makes Dolt Dolt, why we couldn't just go ahead and build on top of SQLite like everyone on the internet thinks that we should have. In case it wasn't obvious, we're the guy on the left there. Okay, so part one is about using the Golang profiler. So the Golang profiler the toolchain is split into two parts. The first part is this runtime / pprof package, and this is code that you have to add to your binary in order to get a profile. And the second part is this go tool pprof tool, which you then run to inspect a profile that was produced by the first part. So you actually have to build this into your application in something that looks like this. Unlike other language runtimes, there's no way to turn on profiling after the fact unless you emit some code similar to this somewhere in your application. You're not going to get a profile out. You have to do it ahead of time. So if you Google how to turn on Golang profiling, you're going to find an example that looks something like this. I'm going to create a file here. I'm going to call start CPU profile on that file, and then run all the main logic of my application, and finally call stop CPU profile. In addition to CPU profile, there's a bunch of other types that are supported, including memory and blocking and Go routines and lots of stuff that you can read about on your own time. For our purposes, we're just going to focus on the CPU profiles today. So that's the most basic way to do it. We recommend going one step farther and using this package profile package that Dave Cheney wrote. And this is just kind of a more ergonomic wrapper around the profiler functions that handle things like temp files, cleaning up when you get a terminate signal, that kind of stuff. So we recommend doing this instead of using the raw profile libraries. And then we also recommend going kind of one step beyond that and building this profiler logic into your application so that you can invoke it whenever you feel like. So this is code that's lifted from the main method of Dolt itself. Here you can see we're looking to see if the first argument to the program is this profile flag. And if so, then we're going to switch and turn on one of several kinds of profiling. So if it's a CPU profile requested, we'll call one method, memory another, and so on and so forth. And it's actually a lot longer than this. I've omitted a bunch of this stuff for clarity. And on the command line, it looks like this. So dolt -- prof, and then we give it the name of a profile that we want to run. So this lets us, whenever we feel like it, just run a profile. We don't have to make any code changes. That's kind of the important part where we're concerned, and that's the main, one of the things I want you to take around this, away from this talk. There's lots of good ways to do this. If you don't want to build flags into your application, or if your application doesn't have flags, then queue it on other environment variables, or some other queue, like running on a particular port or getting a particular HTTP request. My colleague Zach Wasserman had a talk yesterday about how they do this for their Fleet VM's server. But there's lots of good ways to do this, but there's one bad way, which is having to write code and then recompile your application. Don't do that. Build it in ahead of time. Anticipate the need that you're going to want to use profiling. So that's how you get a profile dump file. Let's talk about how to examine that profile with the Go pprof tool. So this pprof tool, as you can see here, the basic invocation is real simple. Go tool pprof, and then it takes a bunch of options in the name of a dump file. My advice to you is just ignore all those options. They really don't matter because the -http option is far and away the best one. Let's look at how it works. Let's do a quick demo here. Okay, so two parts. First, we got to generate a profile dump file, and I'm going to do this by running the CPU, the SQL Server command here. So here's the name of my binary Dolt. I'm giving it --prof CPU, and here's the command SQL Server. When I run this, it's going to start the Dolt SQL Server, and now I'm going to put some load on it. And I'm doing that with a tool called Sysbench. Sysbench is a database profiling tool that a lot of other databases use. It's the primary way that we kind of establish Dolt's performance numbers. In this particular profile, I'm just doing a select star from a table with 10,000 rows over and over and over as fast as I can to kind of illustrate how this works. I have it set to run 20 seconds, so it should finish any moment here. Here you can see the tool says that we've run 123 of these transactions per second. Is that good? Let's find out. Okay, back on this other tab over here, I've Control-C to stop the server. And you can see we've instrumented our program with some logging to tell us where this file goes. So I'm going to copy and paste the location of this profile dump file and paste it into this other command over here. And you see that I'm running go pprof with this -http option. When I start this, it says, okay, now you have a web host on port 8090. Let's go see if that's true. Localhost 8090. There it is. Golang is as good as this word. So this is the default view you're going to be dumped into the first time you invoke this, or the first time you visit the localhost web server for pprof. Looks something like this. This is a view they call the graph view. And as you can, true to its name, it's a big graph of all of the functions in your programs. You can zoom way out and kind of try to get an idea what's going on. The key thing to understand here is that each one of these boxes is a function in your program. And they all have names, and they all give you some information about what's happening inside that function call. So here we're zoomed in on this tracked row iter.next method. This is involved in spooling rows off of disk to return over the wire. And there's two performance numbers here. This first one, 1.18 seconds. That's how much time we're spending directly in this method, invoking code that is actually part of this function. And then 3.9 seconds is the cumulative amount of time that we spend in this function and all the functions that it calls transitively. If I want to break it down farther and understand where that time is going, I follow these arrows. So I zoom in here. Here, this 1.77 seconds tells me I'm spending that portion of the time calling this Prolly row iter.next method. Over here, I'm spending 2.76 seconds calling this table row iter.next method. So you can kind of explore down this graph to your heart's content. The main thing, the thing you should focus on when you first encounter one of these spaghetti plots is pay attention to the size of the boxes. So Each one of these boxes is a function. The bigger the box, the more time your code is spending in that function. So these boxes down here, if I zoom in on this one, this is runtime malloc GC. So I'm spending a lot of time garbage collecting. Then I'm also spending a lot of time waiting on selecting from a channel. That's not great. And then a bunch of time spooling rows from disk, which is great. That's what we want to be spending our time doing. So this is the graph view. It's not my favorite view to use when I'm actually trying to debug performance problems. For that, I find it much more intuitive to use this flame graph view, which I'm going to show now. So flame graph is another graphical representation of where all the CPU time in your program is going. But instead of this kind of spaghetti network of nodes, you just have this nice kind of Gantt chart display. Up at the top, you have a bar which runs all the way across the screen. That's everything happening in your program. And then you can kind of drill down and see which of these functions contribute most to that. So very, very visually, I can see quite easily that this function doQuery.func2 is using about a third of that total runtime, and doQuery.func4 is using about the other, a little over half, it looks like. By the way, this is just what the Golang compiler calls anonymous functions. We didn't name functions func2 and func4. We're not that crazy. But if I want to, I can keep drilling down into this thing and see where the time is going. Here we can see that this is actually Prolly rotor.next is where I happen to know this is where we're pulling rows off of disk to return to the client. And then if we drill down into this func4 method, we can see we're spending a lot of time translating from our internal tuple representation to what MySQL expects over the wire. And then we're spending a lot of time actually spooling those things onto the wire, actually writing bytes to that particular network connection. Okay, so that's the flame graph. Like I said, this is my favorite place to spend time. This is where my go-to when I'm trying to figure out what my program's doing, how it's behaving. The other view that I find useful sometimes is this top view. And this is just a textual representation of from most impactful to least impactful, where is your program spending time without any of with no ability to drill down or figure out what the dependencies between these things are. One thing that I find very useful is you can type in this box here and it's going to highlight for you everything that matches a particular pattern. And this is an easy way to sort through where's my code, what's my code doing versus what library code and parts of the Golang runtime if you want to focus on those things. And all the views we just went over kind of support that same filter capability. It's really useful for particular use cases. There's some other views that you can pull down and play with. But I'm not going to demo them here because, frankly, I don't find them that useful. I haven't really discovered that they've helped me solve real-world performance problems, so I'm not going to kind of waste any performance time going over them. Okay, that concludes part one. So now we understand the basics for how to get a profile dump and then examine that thing. Let's talk about some actual real-world performance profile case studies. And these are some of these things may seem very simple, and they kind of run the gamut of Golang experience. But again, these are all things that we discovered in the context of trying to make our database as fast as MySQL. The first one has to do with interface assertion. So Golang, as I'm sure you're aware, supports a form of interface extension that they call interface embedding. So here we have two interfaces, rowiter and rowiter2. And we want rowiter2 to have all the methods of rowiter1, and then this additional method that we call next2. We're very creative in our naming. And so we just go ahead and embed that rowiter interface in rowiter2. Then at runtime, we have something like this. We've got this iter struct here that has a child iter declared as type SQL.rowiter. And at runtime, we want to assert that it's actually type SQL.rowiter2. So we're making a type assertion converting from one interface to another. We do this in order to be able to call next2 on that reference. So when we did this in performance, we found that it actually was a little bit of a performance bottleneck. Let's dig down into the profile so we can see why. So one of the reasons I'm demoing this one is because it's a little bit subtle. It's not immediately obvious looking at this graph here where the performance bottleneck is, but I'll spoil it for you. It's this box right here. Runtime assert I2I. Which, if you're familiar with the Golang runtime, you know that this is the method that Golang uses at runtime to perform an interface, a type assertion from one interface to another. So the Golang runtime has to look at that pointer that you gave it, figure out, does this point to an object that implements all the methods on this other interface, look up that other interface from a table. So it's doing a bunch of like subtle and esoteric work involved in the Golang runtime. and it's adding up to quite a bit of overhead. So 5.36% of our total CPU cycles are just going to doing this interface assertion, which isn't as big as some other performance problems we've found, but 5% in a database benchmark is a big deal. We want to get rid of it. And I know I said earlier that the flame graph is kind of my favorite way to debug these things, but this is one of the rare cases that I find the graph view actually more helpful. And the key here is that there's so many inbound arrows pointing to this box here. And this tells us that there's a lot of call sites for runtime assert I to I. And here the graph view is doing me the favor of showing me the cumulative impact on my runtime. So if I try to see this in the flame graph view, like I would be tempted to in my first pass, it's actually really hard to see. I have to drill down here. This tiny little box over here is this runtime assert I to I. So because of the architecture of our program, we have a SQL execution graph where nodes wrap other nodes. So a top level limit node is going to limit the number of rows returned. That thing is going to wrap an order by node, which will sort the results. That thing might wrap a group by, which wraps a join. And so you end up with this very deeply nested structure where iterators kind of wrap each other a lot. So we have lots of little call sites that are all paying a relatively small amount of overhead to do these type assertions that add up to a lot of overhead when you look at the whole picture. I think this actually improved. When I originally wrote these slides, you can see that it looked like it was something like 13% of our runtime, and now it appears to be down to 5. I'm not sure exactly why. I'm not sure what changed. We did upgrade the version of Go in the between when I submitted this talk and when we actually ran it. So that's good. The solution to this is really straightforward. You just don't do any of that stuff. If you're trying to make a type assertion inside of a type loop, you should understand that that type assertion is cheap, but certainly not free. So you want to do it kind of once, and then use the new static type of the variable to call the actual method you want. In our case, this means we have 2 fields in a struct that both point to the same object but have a different static type. And again, the only reason we do this is to avoid the overhead. We would love it if we didn't have to do this assertion, but as the Go compiler and runtime exist right now, this is the price we have to pay in order to get better performance. Okay, next we're going to look at various ways of working with slices in your Go programs. And for all these, we're going to be demoing this function called sum array. The first call here is a : rand array, and this thing is going to give us back a big slice full of bytes, and we're going to put them into a sum and then return that thing. So we're going to look at 4 different ways to implement this rand array function, from worst to best, and examine how you find performance problems associated with these things and what they are. So the worst thing you can do when you're building a slice like this somewhere inside of a tight loop that's critical for performance is start with an empty slice and then append into it. There's 2 ways to make an empty slice in Go. You can declare the var like this, or you can call the make method and give it a 0 length. But in either case, you're going to start with an empty slice, and then you're going to call append on that thing over and over and over. And it turns out this is terrible for your performance. Let's look at how bad it is. So here's the flame chart for this run. The first thing you should notice is that my main method here is taking up barely half of my total CPU cycles. I'm doing a lot of garbage collection work over here, a lot of garbage collection work over here. And even worse, if you dig down into this rand array implementation, you can see that runtime.grossSlice is a full quarter of my CPU cycles. So I'm paying this just horrendous cost for allocating my array this way. And of course, the reason that we're calling gross slice a lot is because under the hood, Go slices are array backed. So they're not actually dynamically sized the way that they seem to be. Whenever you try to append an object to it and you exceed the capacity of that underlying array, Golang has to allocate new memory, copy all the old memory over, and do some garbage collection. And it turns out this is a major performance impact, and you should absolutely avoid doing it whenever you can. So a better option, we're going to instead create a slice of a known length ahead of time. So we're creating a slice of length 1,000 here, and then just indexing into it directly with these random bytes. So when I do this, we can see a big improvement. So pay attention from one flame graph to the next. So you can see here the garbage collection pressure has gone down quite a bit. And if I drill down into rand array here, I'm no longer calling grow array. I'm only calling make slice. So I'm using less overhead, or there's less overhead associated with this method of creating an array than there was before. However, you can still see that I'm spending 13% of my CPU cycles just creating slices, just so I can fill them up and then throw them away after I'm done invoking that method. So that's not great either. There's a slight variation to this one, which is not using an interface type. So if you flip back and forth between these two slides, the only thing that they differ in is the type of that slice. So for whatever reason, having to do with the internals of Golang's runtime and how it allocates and tracks array slices and collects them, making a slice of primitive types is a lot cheaper than making slices of interface types. And you can see just how much cheaper by kind of toggling back and forth between these two flame charts. Here you can see my garbage collection pressure has gone down. As well, the impact of make slice went from 13% down to 3%. And the only change here was just using a slice of primitives instead. I'm not going to go into exactly why this is. You can do some research if you're curious. The takeaway is if you can get away with not using a slice of interface types, you should. It's better for your performance. But the absolute best way to do this, there's really no argument, is instead of allocating memory every time you go through that inner loop, just allocate memory once at the start and then reuse that memory throughout the execution. So here we're doing this by passing a slice parameter kind of from the outer scope all the way down to the middle, and then we're going to fill that thing up and reuse it between invocations. There's other ways to achieve the same effect, the most obvious being you're going to use some sort of sync.pool. But the main thing here is that you just don't want to allocate that memory every time you need it just to throw it away. You want to reuse it as much as possible. And when we look at this flame graph, you can see that we've basically squeezed out any sort of garbage collection overhead. We're down to basically, looks like about 97% of our CPU is being used doing actual useful work. So this is great. If I go down to rand array here, there's basically no overhead besides that of assigning memory and creating these random integers. So that's great. To review the worst case thing, so these efficiency numbers that you see on the screen right now, we're going to kind of use the amount of time that the CPU spends generating random numbers as a proxy for how much useful work that we're doing in the program. So to start, we were at 20% of the time generating random numbers to put into that array. And then we work our way up through the various implementations until finally, by the end, a full 70% of our runtime is just creating random numbers so that we can then sum them up. And most of the rest of the runtime goes into doing actual work, summing them up too. So the huge performance impact here, when you play around with slices, be careful how you're allocating the memory and how often. Last case study has to do with using a struct as a receiver. So as you know, when you go to implement an interface in Golang, the most typical way to do that is to use a struct, and the receiver for that struct can be either the struct itself or a pointer to it. You can do either one. Golang doesn't care. In fact, if you at the call site, it doesn't matter if it's a pointer or not. It'll dereference it for you automatically if so. And this is kind of a holy war in the Golang community. You've probably run across a forum post or two. I know how I have. People arguing about whether you should use a struct type or a pointer to it and what the various trade-offs are. But we're all grown-ups here, so we can have a mature discussion about the pros and cons of doing each of these approaches. So with structs, there's this big obvious benefit, which is that they stay on the stack. There's no memory to allocate into the heap that then has to be collected later. So if you have a performance critical application, this might be a good choice for you. It also makes your object immutable in terms of changes made within that method will not be visible back at the call site, which is very desirable for some architectures. And of course, the downside is there's more memory to copy. If you have a large struct, you're going to be copying lots of bytes onto the stack every time you invoke a method like that. Pointers, of course, are just the opposite. There's much less memory to copy around. 8 bytes for a pointer in Golang compared to potentially many more, depending on the size of the struct. And it's mutable. If you need mutability, you have to use a pointer type. And of course, the downside is it goes on the heap. So if you have a application where heap memory management is critical, you're going to be adding to that pressure, that garbage collection pressure, every time you create one of these objects. And of course, it's possible to mix and match in the same interface. Pretty much nobody recommends doing this. There's various style guides and linters that'll warn you if you're doing this and say bad things to you. But I'm a grown man. I lead this project. I can do what I want. So I do sometimes use this pattern in my own work. I find it useful. Okay, so let's get down to brass tacks. Here's a big struct. This thing has 36 fields of various large types, and we're going to go call a method on it over and over as fast as we can. This method all it does is pluck one of these random or pluck one of these float fields from the struct at random and return it. So what happens when we call this thing in a tight loop? Well, it turns out that we're paying a huge performance penalty visible in this runtime.duff copy method there at the bottom right. And you may well ask, what is runtime duff copy? To understand, we got to do a little bit of a aside into computer science history. So in the 80s, a programmer named Tom Duff discovered that you could abuse the C compiler by interleaving these constructs of a loop and a switch statement in order to implement manual loop unrolling. So instead of checking the bounds of a loop every time through the loop, you only check it every so often. And depending what you're doing in the inside that tight loop, this can result in a massive speed up. And computer science history has honored this man by calling this thing he invented Duff's device. It's kind of a horrible C compiler hack that turned out to be quite useful because it does loop unrolling. And if you dug into the source code for the runtime.duff copy method, you will see that it in fact claims to be a Duff's device for copying memory. That's pretty interesting. Researching this talk, I discovered this. I'm like, well, it's not really a Duff's device. Like it's sure it's not. It's copying a bunch of memory around, but it's not abusing this C construct with a loop and a switch. I don't understand why it's called a Duff's device. And it got me thinking. I did some research into Tom Duff here, and there's Rob Pike, Commander Pike on the right there, our patron saint of Go. And you can see that these men have some similarities. Got me suspicious. They're both Canadians born in the 50s. They both worked at Bell Labs after studying at the University of Toronto, and they both worked on Plan 9. So I came away from this research convinced that Rob put a reference to his colleague Tom Duff's work into the Golang runtime, but in fact it's not true. Rob Pike's on my side. This isn't really a Duff's device. The name's kind of a misnomer. It's just a way to copy memory around without doing it in a loop. Sorry, Tom Duff, you don't get this one. But in any case, the solution to this performance problem is trivial. Just use a pointer. This advice comes with a large caveat, which is that your intuition about what's going to be faster, what's going to matter, can often lead you astray. The only way to figure out which is actually faster for your application is to manage it. Sure, you're not going to pay the performance penalty of copying a struct around on the heap or into the stack in order to call a method on it. But depending on what you're doing, that performance penalty might actually be less than the pressure you put on the garbage collector by having pointers. You might also pay some like aesthetic points for not having immutable types when you really want them. So again, the only way to figure this out is to actually measure it and see what happens. Okay, that concludes the case studies portion of the talk. Now we're going to go into a deep dive into the architecture of Dolt database and talk about how it works. And to talk about this, I need to do a brief aside here and talk about the limits of profiling. So there's this thing that happens when you first learn about Golang profiling and you're first trying to make your application faster, where you'll open up that performance profile and you'll see a big red node in the middle of that graph. You say, aha, and you smack that thing with a hammer and your code gets a lot faster and it feels really good. It gets to be this kind of addictive loop that you can get into for days or weeks, and I've done this myself, where you just get stuck in performance land, smacking things with hammers and breaking up performance bottlenecks. And it feels so good, you want it to go on forever, but it can't go on forever. There's limits to how much the profiler can improve your code's performance. This is just kind of the nature of the beast here. You start off with the lowest, juiciest looking piece of fruit, and then you pull that thing, and then each piece of fruit that you pluck afterwards is slightly less juicy and slightly less impactful to performance. And so you end up with this pattern of diminishing returns. We can see this illustrated in the graph in the bottom left here. These are actual numbers that my colleague Max discovered when he was making a round of performance improvements to how Dolt manages joins, index joins in particular. And you can see at first he's making these massive improvements, and then over time, it's getting a much harder to squeeze more juice out of that lemon until eventually we're way inside of diminishing return land, and we need to make bigger changes. And so writing our own database is hard. We're not smart people. We shouldn't have done this. But we had this dream to build the world's first version control database that we're trying to do for all of you. So we're dedicated to it. But when we went to start making it faster, when we decided we needed to care about performance a lot more than we had in the past, we ran into this situation of diminishing returns. We picked all the low-hanging fruit, and we were still a lot slower than MySQL, still over 5 times slower than we needed to be. So we ran into this wall. And this is when we had to switch from a particular mode that I'll call kind of performance optimization into a different mode that I'll call re-architecturing. So we'd kind of milked all the gains that we could out of a substandard architecture, one that wasn't doing what we needed it to. And at this point, we had to stop trying to make what we had incrementally faster and radically change how we were approaching the problem in order to get any further performance improvements. So to understand what I'm talking about here, we have to talk a little bit about how Dolt works. So buckle in for that. Let's start with B trees. So B trees are the data structure that's common in computer science. It's very common for databases. It's how basically every SQL database since Oracle and Postgres and before have stored their data both in memory and on disk. The B doesn't stand for binary. I don't think anyone actually knows what it stands for. But it's like a binary tree in that you start at the root looking for a particular value, and to find a value, you do comparisons, follow the appropriate child node down the tree until the value is either there or it isn't. And for Dolt, we use a slightly different data structure that we call a Prolly tree. So a Prolly tree is this kind of spiritual cousin to a B tree. It has a lot in common with a B tree. The data is still stored indexed with its key values, so you can walk the tree in order to figure out whether a value is in that tree or not. But it has a couple key differences that are really important and are what makes Dolt Dolt. So first of all, you'll notice these black and orange numbers. These are the cryptographic hashes of these nodes in the tree. Uh, the, the, the reason this is important is because Dolt is a version controlled database, which means we support operations like diffing 2 revisions of your database. So if we have 2 of these trees that represent 2 revisions of the database, and we want to understand which parts of the database, which rows in it are different, all we have to do is start at the top of the tree and start walking down. And at any point, if we discover that 2 of the children have the same cryptographic hash, we know that that part of the tree is equal, and we don't have to descend into it and look at it. So this is the key realization, the key insight that makes efficient diff and merge possible, is that we've hashed all these nodes, and we can tell without examining them closely at all whether or not 2 nodes are identical. That's the first one. The second one is that you'll notice each of these nodes have a different number of children in them. So the top node has 3 elements. The one on the bottom left has 1, and in general the number of elements in one of these tree nodes varies pretty dramatically, and this is on purpose. But it's not but it's not known ahead of time. The Prolly in Prolly Trees stands for probability. So in order to build up a Prolly tree from scratch, in order to understand where to put in which nodes to put particular child elements, we run this probabilistic function. So on the bottom line of this diagram, you can see there's a bunch of numbers we're inserting, 1, 2, 5, 6, 9, etc. And on the top row, we're going to be taking a hash of those numbers as we insert them, and we make this rule. The rule is whenever that hash falls below some threshold that we choose, that's where we're going to draw the line and say, that's the end of that node, now we're going to start a new child node. What this gives us is a probabilistic distribution of various node sizes that have a very important property for when it comes to structural sharing. So again, we're a version database. Whenever you make a new commit, we're going to store a snapshot of the old database and a snapshot of the new database. And it would be a really bad idea if every time you did that, we had to double the size of storage required by storing an entirely new snapshot. What we want is this principle of structural sharing. So in these diagrams, the blue blocks introduce or represent new information, new nodes being inserted into the database, and the gray ones represent the stuff that was there before. So our goal here is to be able to maximize the amount of data that is shared between 2 revisions of one of these trees so that we don't have to blow up storage as you store new revisions of the database. That's what the probabilistic child or the probabilistic node size does for us, is that we find that on average, when we go to insert something in one of these nodes, we don't change any boundaries within it. We don't have to spill those changes over into the rest of the tree. If you imagine like a very bushy, full B tree that you go to insert a value into, that node is full. What do? Well, you can either increase the depth of the tree, which is bad for your performance, or you can rearrange the tree, which is bad for your structural sharing. So Dolt's Prolly tree implementation kind of merges these 2 advantages so that most of the time when we do an insert, it's cheap. We're touching that node, we're touching all of its children back to the root, but we're not, those changes aren't spilling over into the rest of the tree and causing us to blow up our storage costs as we create new revisions. And here you can see this is true whether we're doing a single insert in the middle, a bunch of values at the end, or at the beginning, or in the middle. We get this nice structural sharing impact because of Prolly trees. So we didn't invent Prolly trees. We very luckily kind of found them lying around disused. in this project called noms. This is the noms otter you can see on the screen here. Very adorable mascot. Noms is this database that provided us with our first implementation of a Prolly tree. And in fact, the reason that we wrote Dolt in Golang in the first place, despite none of us knowing Go at the time, was because this implementation was around lying there for us to use. And it would have been much more difficult for us to develop our own Prolly tree data structures from scratch. So we built on noms to get kind of a head start and get a proof of concept up and running and get some people using it. But as we went on with the database, and especially as we turned our eye to performance, we began to understand that the architecture of noms left a lot to be desired for kind of three reasons that I have on the screen here. The first is that noms is very general. Noms is a graph database. You can store all sorts of exotic data structures in it, things like maps, lists, sets, structs, all these things that we don't, as a tabular database, don't have any need for. We're storing table rows. We don't need all these exotic databases. We query it with SQL. We don't query it with a graph query language. So these are all pieces of functionality that we didn't need and were hurting our performance. The reason that it hurt performance is that this type of general graph storage capability makes everything very expensive to serialize and deserialize for reasons we'll get to in just a second. And because things are so verbose, that in turn limits the branching factor when we're storing one of these trees. Generally speaking, you want as great a branching factor as possible so that your trees are as shallow as they could possibly be. The deeper your tree, the more expensive it is to do any particular insert or lookup operation. So we ran into these limits with the noms architecture and had to come up with something different. Here's how we're storing table data in the old noms format. I said before that noms represents maps as kind of a first-class citizen, so our first pass through this was to store table data as a map. And particularly, we store it as a map from all of the key columns and their values to all of the non-key columns and their values. And you'll notice that we're intermediating with this tag number. Rather than storing the name of the column, we store a tag number that represents that column. Simply just because it's cheaper to store an integer than it is to store a string. It has some other nice storage properties. But this is basically how it looked beforehand. We're storing our table data as rows or as entries into one of these map data structures. The problem is these map data structures don't serialize down very cleanly to something that's performant for us to pick up and use. And this is in large part because the type system of noms is self-describing and very verbose. So this is how noms defines a commit struct. You can see that the type of this parents field is a set of refs of cycles of commits. Very general, it's self-describing, but it's very, very verbose when you actually get down to deserializing one of these things. So here's how they're laid out on disk. Here's all the bytes that go into the serialized form of one of these objects, and you can see that they're laid out in these triples. So you've got the type of a particular object, its length on disk, and then the serialized bytes of the value. So when we go to deserialize one of these maps, when we're doing a lookup on a table row, we have to parse this whole thing, pull it off of disk, and make sense of it. And because we have to, as we go, read the type and the length, instantiate a deserializer for that type, and then repeat that for all the elements of the array, we ran into a lot of overhead. In particular, there's linear access time for any element because we don't know where inside this big data structure to look for any particular element. We have to read and understand the entire thing in order to compute the offsets ourselves. This was a major performance penalty for us. We decided we could do better than this and introduce this new tuple storage format. We did a couple major pieces here in addition to making it just more compact. The biggest impact here is that the types are stored out of band. So unlike noms, when you encounter one of these objects lying around on disk, you can't just read it and understand what's in it. You have to have the context. You have to understand what you're looking at in order to read it, but that's fine for us. That's a fine performance trade-off to make. So we store the types out of band. You have to know what the types are when you go to interpret one of these things, or else it doesn't make any sense to you. The other big change is that all of the offsets are stored at the end of this byte array. So the very last element is going to be a count of the number of fields. Once we know the count, we know exactly where to look inside of that array for the offset for each one of those elements. Once we know the offset, we know exactly where to look inside the array to read the value payload. So this gives us constant time access inside of a row without having to do any sort of without having to loop over the entire array and actually understand what's inside of it. This is a huge win for us. But probably an even larger impact for us was changing how we store these things. The non-serialization format was kind of its own handwritten thing with its own parser. Very slow for a lot of reasons, not just its verbosity. When we were looking around for things that we could replace it with, we found this flat buffers library, which is kind of this cousin of protobuf. Like protobuf, it's written by Google, and it has this textual representation that you can use where you describe your data format, and then you run a tool and it generates bindings in all the languages you might care to use that know how to get these things off of disk and into memory and vice versa. But the really cool thing about flat buffers, which sounds too good to be true, but actually is there's zero deserialization cost. So flat buffers has this property where the way that the data is laid out serialized on disk is effectively the same as the way it is laid out in memory. All you have to do is slurp up the bytes from disk, say that now it's a type of this struct in the language of your choice with some unsafe pointer math, and you have an object ready to go. There's no actual deserialization cost. It's kind of magic. It looks like this. Here's a Prolly tree node written as a flat buffer. You see we've got an array of key items and their offsets, and then an array of value items and their offsets, and some other bookkeeping stuff in case this is an internal node. We have to figure out how to follow children. But at the end of the day, it ends up with this massive speed up. So here's benchmarks of the old NOM serialization format compared to flat buffers. And then kind of for fairness' sake, we also wrote a quick protobuf implementation to try to kind of see how it compared with other open source alternatives. The upshot here is that compared to NOMs, flat buffers has 10 times the speed when you're reading one of these things off of disk. So that's a huge win. Protobuf is also a lot faster than the NOM serialization format. But the flat buffers implementation was still about 30% faster than protobuf. And the big win for us came in terms of memory allocated. So if you look at that third column across, we went from doing 21K per of allocations per read of one of these nodes down to 500 bytes. This is a huge win, and even compared to protobufs, we're doing 90% fewer allocations, fewer bytes allocated. For us, this is really important. We're running a database server. We need to keep allocations to a minimum to keep garbage collection pressure down, because that steals performance from all of our threads doing actual work. We can see these numbers. So at the end of the day, this is what we ended up with. When we the number on the left, 5.2, is what factor slower than MySQL we were when we started this re-architecture rewrite project. This was after we'd done a bunch of performance optimizations with the Golang profiler tools. We started about 10 times slower than MySQL. We were able to get that number down in half just by kind of tightening that code in our existing architecture. But we couldn't get any farther than that. To get past it, we had to actually do this rewrite at the storage layer that we've talked about. We measure ourselves against MySQL basically because we bill ourselves as a drop-in replacement to MySQL. We speak the MySQL wire protocol. It should be a drop-in replacement. You can just take an existing database application and swap the backend out, and it still works. And this is what customers want to know: how much, what performance penalty are we paying by switching to your database product? So we run all these benchmarks that are industry standards and compare ourselves as in terms of a multiple of MySQL speed. So again, we started this rewrite process about 5 times slower on reads and ended up 2.5 times slower. So a huge win there. On writes, the difference was even more dramatic. We started 12 times slower than MySQL and eventually got that number down to 3. And we summarize this overall as a 3x overall speed up, 75% reduction in writes, 50% reduction in reads. So we're feeling pretty good about this. We're now kind of within what we consider striking distance, where people don't have a good performance reason to prefer a more established database to us. We know we can eventually close the rest of the gap and be as fast as these much more mature, established competitors. There's a lot more work to be done here. Most of the talk, or most of the effort that we've focused so far, is just in terms of the raw speed of reading these things off of disk and writing them back to disk, because that was kind of the bottleneck we ran into first. But there's a lot more work to do in terms of transaction speed and general overhead in our SQL execution engine. So we do think that we're eventually going to close up and maybe even draw ahead of MySQL or Postgres or something like that. That's all I got for you today. I appreciate everybody coming to the talk. If you want to learn more about Dolt and the company, we've got a couple of URLs on the screen that you can visit. Please check out our open source repo and give us a star. We always like it when people do that. If you want to talk to me, I'm going to be around here after the talk. Or you can ping me in the talks channel on the GopherCon Discord. Always happy to meet new people. Really appreciate your time. Thank you for coming.